All right, today we're going to dive into the beautiful and sometimes, let's be honest, pretty bizarre world of complex numbers. We're going on a little journey to a hidden side of mathematics, a place where the rules you thought you knew get bent, and where imaginary numbers can lead to some surprisingly real results. So let's get into it.
Our central mystery for today is this question right here. What in the world is I to the power of I? I mean, logically, you think the answer has to be complex or imaginary, right? But the truth is so much stranger. The answer is a real number, and by the end of this, you're going to understand exactly how that's even possible.
Now, to solve this puzzle, we can't just jump straight in. First, we need to build ourselves a toolkit. We have to see how some familiar ideas from math, like functions, behave when we take them out of our comfortable little number line and into the wild world of the complex plane.
So let's start with something you've definitely seen before, a function. The easiest way to think about it is like a machine. It's just a rule. You put something in, we'll call that an input from some set A, and the machine follows its rule and spits out exactly one output in another set B. That's it. Simple as that.
And of course, we've got special names for those sets. The domain is just all the stuff we're allowed to put into our function machine, and the range is all the possible stuff that can come out. So domain is the input, range is the output. Got it? Okay, here's where we make our first little leap. What if the inputs and outputs for our machine aren't just regular numbers, but complex numbers? Well, that's all a complex function is. We're not changing the idea of the machine, we're just swapping out the kind of numbers we're feeding it.
So it turns out there is this one incredibly powerful formula that connects these huge, seemingly separate areas of mathematics. It's like a master key that unlocks how things like exponentials, trigonometry, and imaginary numbers all secretly talk to each other.
And here it is. This is the hero of our story, the complex exponential function. Now, I know it looks a little intimidating, but the idea behind it is so powerful. When you raise the number e to a complex power, z, which, remember, is just x plus I times y, it kind of magically splits into two parts. You get a real part, e to the x, that scales things up or down, and then you get this part with sine and cosine that literally rotates things around. This connection is our master key.
And check this out. Watch what happens when you plug in a really specific value. If you make z equal to I times pi, that big master formula just collapses into this perfect little equation, Euler's identity. It connects the 5 most fundamental constants in all of math, e, I, pi, 1, and 0, in one beautiful statement. This is proof that our key really works.
So, armed with our master key, we can now do something amazing. We can uncover the secret identity of functions we've all known since high school. It turns out sine and cosine, they're not really about triangles. Nope, that's just one of their disguises.
So how do we unmask this secret? Well, we start with a version of Euler's formula. You can see it in step 1. Then we grab its partner for e to the negative ix in step 2. Now, just watch what happens when we add them together. The I sine x and the negative I sine x, they just cancel each other out completely. A little bit of rearranging, and you find that cosine isn't really fundamental at all. It's actually just built out of these complex exponentials. And this leads to a pretty mind-bending question. We were all taught in school that cosine has to be stuck between -1 and 1, right? But if it's secretly made of exponentials, does that rule still apply in the complex world? Could we actually find a complex number z where the cosine of z is 2?
Well, to find out, we just set our new exponential definition of cosine equal to 2. We do a little bit of algebra to clean it up, and look at what we get. It's a quadratic equation, like from high school algebra. But the variable isn't just x, it's e to the power of iz.
And when you solve that quadratic, you get this absolutely astonishing result. The answer is yes, cosine can equal 2. And this is just a perfect example of how weird and cool complex functions are. We had to plug in a complex number, one with an imaginary part, to make it work. But the output is a perfectly real number that we were always told was impossible. Okay, so that result with cosine shows you just how powerful these new definitions are. And we are so close to solving our main puzzle, of I to the I. We just need to add 2 final tools to our kit. And guess what? They also come directly from our master key, that exponential function.
First up, we need the opposite of the exponential function. And that, of course, is the logarithm.
If the exponential function takes an input w and gives you z, the logarithm is just the tool that takes that z and tells you which w you started with. It just undoes the exponential.
But here's where things get really, really strange. In the real world, the natural log of 1 is just 0. That's it, one answer. But in the complex world, it's a whole different ballgame. Remember how the exponential involves rotation? Well, you can land on the number 1 not just with 0 rotation, but after 1 full rotation, or 2, or 3, or 100. Because of this circular nature, the complex logarithm has infinitely many possible answers. The log of 1 could be 0, or 2 pi I, or 4 pi I, forever.
And now for our final tool, the general power formula. This is actually how mathematicians define what it even means to raise one complex number to the power of another one. And look closely. It's built using our other tools. It says that a to the z is really just e raised to the power of z times the natural log of a. This is the formula that's going to crack our problem wide open.
All right, the toolkit is complete. We have our definitions, we have our master key, we have our formulas. It is time. Let's put all the pieces together and finally solve the mystery we started this whole thing with.
So we start by just applying that general power formula directly to our problem. We want I to the power of I. So we look at our formula, we replace a with I, and we replace z with I. And that gives us our starting point. I to the I is equal to e to the power of I times the natural log of I.
Okay, next up we've got to deal with that natural log of I that's up in the exponent. Now, as we just learned, the complex logarithm has a ton of answers. But for now, let's just focus on the main one, the one mathematicians call the principal value, which happens to be I times pi over 2. So we're going to take that value and just substitute it right back into our exponent.
And now for the magic.
We just need to simplify what's up in that exponent. We have an I from our formula, and it's being multiplied by another I from the logarithm we just figured out. And what is I times I by definition? It's -1. So in that one single step, all of the imaginary units, the i's that we started with, they just vanish. They're gone, leaving us with only real numbers.
And that leaves us with this incredible result. Our original, completely imaginary question, what is I to the power of I, is equal to e raised to the real number power of -pi over 2. You punch that into a calculator and you get a very real, very tangible number, about 0.20788. No imaginary part whatsoever. A purely imaginary question gave us a purely real answer.
So what do we learn on this whole journey? Well, we saw that complex functions take these simple ideas we already know and give them a whole new amazing life. We found out that the exponential function, e to the z, is like the master key that secretly connects everything. We learned that in this new dimension, old rules can be broken, and cosine can totally be greater than 1. And maybe most importantly, we discovered that even the most abstract imaginary-sounding questions can have concrete, real answers.
Which really just leaves us with a final thought, doesn't it? If something as weird as I to the I can turn out to be a simple, real number, it just makes you wonder, what other beautiful and profound connections are still out there, hiding just beneath the surface of the math we think we already understand? Thanks for watching.